Okay. So I got an email from the person in charge of the college colloquia who is gathering us on Thursday because large numbers of students in the college colloquia are not turning in work on time and at risk of failing. And why do I tell that to this section? I need to look back over things. It looks to me like I got roughly half of the midterms in on time. No one has convinced me I shouldn't grade those according to the syllabus, which would mean that they are worth 0 points. And the thing that convinced me that those are worth 0 points is I read all of them, and I think I have already spent more work trying to give them a higher score than 0 than many of the submissions. What is motivating this is the credit hour policy for this university, which we have to follow, or we're going to get in trouble with now the United States federal government. It says you have to spend 2 hours outside of class for every hour you spend inside class on this homework. I wrote out a midterm that I thought it would be impossible for not every student to do, probably early, which is to write 2,000 words and turn in code that we'd spent 8 weeks writing together. I also think it was possible to do that. As I showed you last class, I gave you examples of student work that completed all of the requirements quite well. Many of the submissions completed not even most of the requirements and also would have probably gotten no points on the AP scale rubric because they weren't at college level and they didn't have the minimum word count. Anyways, let me show you the syllabus real quick, and I'm going to show you how this is going to work for us in real life. I did give everyone an A last year, even though they didn't turn things in, and I got in a ton of trouble. So that's probably not an option. Okay. So the way I set this out at the start of the term is that there was a distribution in between exercises and papers. How does this work? Okay. There are, how many weeks in this term? I think there are 15 weeks. SciComm. There are 12 weeks. And then of those 12 weeks, there are 1, 2, 3, 4, 5, 6, 7, 8. Oh, we'll say 9. Oh, yes, there's 9 because there's 9 up here. There are 9 exercises. The exercises you get credit for attending class. That was my baked-in curve. So all of you are going to get 100% on 9 exercises. There are 9 exercises of equal weight. There is a midterm weighted as 3 exercises and a final weighted as 6 exercises. I will drop the 3 lowest scores and take the top 15 scores. What this means is that if you were in the population that, in my view, either did not turn in a midterm or turned in a midterm so close to no effort, I don't feel good about giving it a score higher than a 0. Those will simply be your 3 lowest scores, and they will be dropped, and your grade will be basically determined by your final, and it will essentially be curved by the 9 exercises getting 100% of the score. So what is 9 out of 15? It's about 66%. So you will get a 66% in this class plus your score on the final, and the remaining 1/3. What is some of the motivation for actually applying the grading scale right now? I've taught the college colloquium a few times, and again, for accreditation reasons, which means I am legally required to do this, I have to stop accepting work in this class at like whenever the obscure time in the semester the class actually ends is, which I think is Monday 11/17. Is that right? So that means if a final is turned in after that grade, I am not allowed to grade it for that semester unless you take an incomplete. And if you take an incomplete, we have to go to like academic council and like actually give them a reason, right? So if a final is turned in late, I don't know how I can give you higher than a 66% in this class without changing the syllabus. And then I have to explain to someone why I'm changing the syllabus to give students that didn't turn in work a higher grade. Okay, so I've decided to be mean. I'm zeroing half the midterms. I'm going to put them in Canvas. I'm going to put in the grade I would have given you if it was turned in on time, and then I'm also going to give you a turned it in on time score. I'm going to drop the highest in the midterm category so you'll see both grades, and it'll show up on Canvas and you can see where you are. Please actually do and turn in the final. to me and let me know if this is unreasonable because I would like you to succeed. I posted what the midterm and final were literally before the first day of class. I showed you them on the first day of class, and I've been, I thought, teaching you things that were necessary to do these successfully the entirety of the term. This has slightly more requirements. It has 3,000 instead of 2,000 words, and I have to teach you one additional technology, which is Quarto, which is what you saw for the example midterms. This is here. This has been posted. It has been posted forever. And I am confident in your ability to do this. We will have a collective learning experience, and then you're all going to turn in a final. I have provisions in the syllabus to drop low scores, but you please actually turn in a final that meets the minimum requirements. I have a limited ability to give people good grades that don't turn in work. Okay, does that make sense? Okay. All right. I am now going to teach you about symbolic Python. Okay. Symbolic Python is cool and fun. I was actually using it in one of my other classes. Okay, so.
Are you a week ahead?
Am I?
Yes.
What week am I supposed to be on?
SymPy.
SymPy, yes. Oh, they both start with S. Oh my gosh, okay. Thank you. All right. Dang it, I wanted to do symbolic Python today. SymPy. My partner is a chemist, and so she does real science, and she's allowed to call this whatever she wants. She calls this Skippy. You know how there's Numpy and Skippy? So this is, you can call it Skippy if you're a real scientist. And so I think many of you are chemists and biologists. You're allowed to do whatever you want, right? But if I hear a mathematician call this Skippy, I'm going to be mad, right? Okay, so what is Skippy? It's pronounced SymPy. It's even on the slide, see? It is an open source software for mathematics, science, and engineering. It is short for scientific Python, which is very odd because numerical Python was originally going to be the thing for scientific Python. But they called it numerical Python for some reason. So it's basically a NumPy extension. NumPy, which you've all used, is sort of in this like Goldilocks zone between being too heavyweight for anyone to use it and being too light to do anything useful. So SymPy has all of this stuff they left out of NumPy so people would actually use NumPy, but it's all NumPy compatible. So it's meant to all work together well. SymPy was, I think, mostly only used in like very specific cases in the sciences for quite many years until it became the basis of something that is very important, which is the scikit-learn library. The Sci in scikit-learn stands for the Sci in scientific Python. Kit means it is part, so it intended to be part of SymPy, but it's an extension, so it's an additional thing. And learn stands for machine learning. This is the most popular machine learning framework in the world. This class has the name Thinking Machines tacked onto it, and so as we go from NumPy to SymPy to scikit-learn, we are getting closer and closer to the machines thinking themselves, right? So we're building up to that. Versus many other libraries I've seen, if you look up the SymPy documentation, which I don't necessarily think you need to spend your time doing, but if you click into here, and let's see, it's going to take a while to load. Many of the functions and formulas and equations that are implemented in scientific Python actually have a peer-reviewed citation for how they are implemented. So it's actually a component of scientific research, a component of what is happening with the internet today. User guide? Any of these things going to work? So, for example, if you're like, oh, I need to calculate a population or a predator-prey relation populations, right? There will be citations, academic citations to papers that are published by people trying to get tenure or trying to get their doctorates that actually described these equations and implemented them in scientific Python and tested them and published them and went to conferences and defended their work and then implemented it in the scientific Python library. So it is unusually scientifically rigorous, right? All of the code has to work. It all goes through testing. But this is also tested by scientists to make sure it does what it says it does. Why would we not use SymPy? Well, SymPy has really one big challenger, which is that a lot of things that SymPy is used for is doing statistics, So if you are doing human systems research, if you are doing survey results, if you are doing public health, medical to me does not seem to use SymPy that much. So some of you are looking at the medical and health sciences, you might use one of its competitors. And the big competitor is stats models. Stats models does a subset of the things SymPy does. It does the statistical subset, and in my opinion, it's a little bit easier to work with if you are not using any of the things outside of stats models. So I could just as well teach you stats models. Why would I not teach you stats models? I would like to teach you scikit-learn, and to my knowledge, all the people in health and medical are now also using scikit-learn. So there's sort of been a trend away from stats models over time for that reason, though now they all just sort of play nicely together. SymPy is often more than you need. We have done some pretty interesting things, I think, this term using NumPy. And for me, actually, when I put these slides together, it was actually kind of hard to find things to do with SymPy because I usually don't need all of that stuff. I don't know what you're going to need it for because I am not a biologist or a chemist or a physicist. And so when I see this thing that's like, oh, this is used in this application in physics, I'm like, I don't know what that is, right? I came up with a few examples that I think are interesting, and mostly they're just to get you familiar with the library, and hopefully if you ever need to do something interesting, then you'll be able to do so. That is to say, I use NumPy and scikit. I use NumPy every day. I use scikit-learn every time I'm trying to do statistics. I don't use stats models in SymPy anymore. And I have never used SymPy in my life. But I do know that it's historically important. The two most scientific computing things that have ever scientific computing, to my knowledge, are signal processing and interpolation. And I'm going to explain briefly what I mean by both of these in a minute. I actually have to look at my time so I don't run out of clock. So I'm going to try and point. And if I point at just the right angle, I point to Professor Jed Rembel's office. Professor Jed Rembel has a doctorate in physics and taught in the physics department for many years. And Professor Jed Rembel does astronomy. So why is Professor Jed Rembel now in the computer science department? Well, because all of astronomy now is done by taking instruments, plugging them into computers, and then writing code about the information that comes in from the instruments. And what are these instruments? Predominantly, to my knowledge, and you can ask Professor Jed Rembel, they are radio telescopes. So I point an antenna at space. It measures radiation coming out of the sky. And from looking at that radiation, it can tell things like, I don't know, like how old the universe is or something like. I don't know what physicists do, right? Importantly, as soon as you finish building the radio telescope, the only thing you're doing is programming here. So, yes, it's not like computer science in the classical sense of like, oh, I'm going to do an algorithm. It's not like software development in the sense of you're making a website, right? But it's all on a computer, it's all typing, it's all in sort of the scientific computing world. That's signal processing. I've got this information coming in over the wire about some physical or naturalistic phenomenon I want to study, and I'm going to use a computer to understand it because there's no practical way to do it manually. I can't just listen to the sky at night and figure out what the radio telescope is hearing. Now, you can actually play the sound from radio telescopes, but that doesn't help me at all either. It sounds like nothing to me, right? The other thing is interpolation. Sometimes you take a series of measurements or you collect some data and you're missing some things. And you want to make an informed decision about what you're missing. Scientific Python has a series of interpolation libraries that allow you to guess what data you're missing. This has historically colossally stressed me out, and I don't really trust the citations on this, but I'm going to show you an example of how this works and how this doesn't work on Friday. And so that's what we're going to work on that day. And we're going to do it with technetium, the synthetic element in the middle of the periodic table. Okay. SymPy is big, and I had to look at all of these things. So here's the user guide, here's the API reference, and here's the cookbook. Yes, what is your question?
I still don't understand. What exactly is interpolation?
So if you know the temperature 6 days of the week and you want to guess it on the 7th day, you would interpolate. It'll make more sense when we have an example, because usually it's not just like linear like that. So I think the example I use is, say we know the density of every element on the periodic table except one. Mm-hmm. How closely can we guess that last density?
So I guess
yeah. And I think it's called interpolate. The inter means in between data you know. I don't know what polate stands for. It appears that the SymPy documentation is down today. So, oh, this is up. The cookbook is up. And we'll see some things that we've heard of before, where, for example, Matplotlib is clearly featured here. Here's interpolation. Let's see if they tell us what interpolation are. Nope, not at all. They just give us some examples. Here's an example of how to use B-splines and SymPy signal to do interpolation. Yep, that didn't help. That didn't help. Okay, that's okay. Install. It is time to install SymPy. So, how do I install SymPy? I don't even know if I have it on this device. Let's see. Function of 11. Okay. Python 3. And if I'm on Windows, I type Python instead of Python 3. -m for module. What is a module? It's like a Python file. And I'm going to use the pip separate command to install Skippy. And this will take a minute. It appeared to not take me that long. Has someone started it? Is it slow? I expect this to be slow. SymPy version. Okay. That was fast. I expected that to be slower. It's going okay. I don't need help with anything. Speak now or forever hold your peace. Okay, cool. It is not too difficult to verify your SymPy version. I showed a command line based way to do this. I will show you this and narrate it just because I wrote it in front of you, and then we'll go to the other way. Let's see. Okay. So I can type Python 3. I can use C to give a command directly at command line. Then I can write some Python inside of the quotes. I'm going to import SymPy. I'm going to use a semicolon to line break. Usually I would line break here, and maybe I can even do this. I'm not sure. Print SymPy __ version. And we've used the double underscores in the past with things like NumPy and so on. Oh, and I have to close my quotes. So that is one way to do this directly at command line. Maybe that's unnecessarily convoluted. So instead, let's see. Do I care about any of these things? Okay. So what I'm going to do instead is I'm going to make a little file, and I'm just going to check to see if I have a SymPy version by running that. So we'll open NeoVim, and I'll make, I'm going to call it Skippy. No, I'll call it skip.py, Skippy. And I will just copy paste over these lines that I have here. I will save and exit, and then I can run Skippy, and it will tell me what version of SymPy I have. So this is how I can make sure I have it. And oh, that's interesting. I guess I have a very old version over here versus this one. And that's okay. I think probably any version 1 is fine. Is someone on Mac?
I am.
What version do you have on Mac?
I'll check. Just do the slide up when it runs anything.
I'll go through the example of what I did again.
1.16.2.
Ooh, 16.2. Wow, that's the newest one so far. Okay. Anyone on Windows? What version do we have on Windows?
Also 1.16.2.
You also have 1.16? All of you have 1.16 except me? I'm showing my age. Okay. Is my hair going gray? I think it was. Last time I cut my hair, there was a bunch of gray under it, which I didn't know.
When did you get a haircut?
I got it. I went home from class yesterday, and got a haircut because I had to give a talk the next day, and people had started making fun of my hair. But now they're making fun of this hair, so I don't know what they want.
Why were they making fun of it?
So,
Gangnam Style?
yeah, we're gonna do Gangnam Style. I think it's like fun to make fun of other people's hair, right? Okay. I'm streaming on YouTube, so am I gonna click that link?
Nope.
Nope, that link is gonna stay blue because I don't want to lose my account forever, right? But I think we all know what Gangnam Style is, right? Ooh, I don't even know if I can play it. Can Can I pause this? I'm just going to mute everything.
I mean, you can click this.
Going. I'm going to mute the desktop audio. Okay. No screen. Okay. I think this is fine.
I have not seen the animation.
We haven't seen the animation. Wait, is it muted?
오빤 강남스타일 강남스타일 낮에는 따사로운 인간적인 여자 커피 한 잔에 여유를 아는 품격 있는 여자 밤이 오면 심장이 뜨거워지는 여자 그런 반전 있는 여자 너는 선호해 낮에는 너만큼 따사로운 그런 선호해 커피 식기도 전에 원샷 때리는 선호해 밤이 오면 심장이 터져버리는 선호해 그런 선호해 아름다워 사랑스러워 그래 너 바로 너 아름다워 사랑스러워 그래 너 바로 너 지금부터 그때까지 오빤 강남스타일 강남스타일 오빤 강남스타일 강남스타일 오빤 강남스타일 섹시 레이디 오빤 강남스타일 섹시 레이디 성숙해 보이지만 놀 땐 노는 여자 이때다 싶으면 묶었던 머리 푸는 여자 가렸지만 웬만한 노출보다 야한 여자 그런 감각적인 여자 나는 선호해 점잖아 보이지만 놀 땐 노는 선호해 내가 되면 완전 미쳐버리는 선호해 근육보다 사상이 홀통벌통한 선호해 그런 선호해 아름다워 사랑스러워 그래 너 바로 너 아름다워 사랑스러워 그래 너 바로 너 지금부터 그때까지 가볼게 오빤 강남스타일 강남스타일 오빤 강남스타일 강남스타일 오빤 강남스타일 섹시 레이디 오빤 강남스타일 섹시 레이디 위는 놈그 위에 나는 놈 베이베 베이베 나는 뭘 좀 아는 놈 위는 놈그 위에 나는 놈 베이베 베이베 나는 뭘 좀 아는 놈 오빤 강남스타일 섹시 레이디 오빤 강남스타일 섹시 레이디 오빤 강남스타일
You can probably notice the ankle mobility exercises inside the video, right? This one? Yeah. Okay. So I hope we all learned from that.
That one dance is iconic. I saw that once as a little kid and I've been able to remember it ever since. Yeah, it's
Skippy. Okay. Anyways, this is scientific computing. Okay. Do not click this link. Oh, look, I made a note to myself. Okay, cool. All right. Let's turn everything back on. We'll find out if we went to jail later. Okay. Well, I mean, we can... I'm not in trouble yet. See? Stream health. This does not say you're in trouble. Okay. All right, so Skippy, I gotta stop saying that. SymPy has the ability to read. I also eat Skippy peanut butter, so it's like it's two things, right? It's getting. It has the ability to read some file types, but not others. And so, what's a file type? Well, you've seen .py files, you've seen .txt files, you've seen Markdown files, right? Another relatively famous file, and this file I believe is used relatively commonly in scientific computing. I've definitely seen, for example, whale sounds captured in this way, is the .wav file, which is a waveform audio file format. SymPy does support the waveform audio file format, and it does not support reading directly from YouTube URLs, probably because, well, I'll tell you what I'm not about to do, which is I'm not about to teach you how to steal music off of the internet, right? So since that's not what I'm doing, that's not the application here. There are a combination of tools that we can use to take Gangnam Style and put it into Python and do some changes to it. So I'm going to show you what some of them are. One of them is the Python package ytdlp, which, do I have that one? I apparently do have that one, but I think if I python 3m pip install ytdlp, you're able to install that package. That one's easy. The one that's really hard to get is ffmpeg, which translates MP4 files, which is the video file format that I usually download YouTube videos into .wav files. I didn't find that one particularly easy to find, so I'm not necessarily going to require you to do any of that, and I'm just going to donate the WAV file to you. I can probably play about 5 seconds of this, but this is a .wav file embedded in a slide. You know, I'm going to mute. I don't want to lose everything I love. Okay, we'll go ahead and I'll just mute desktop audio for the rest of class because I don't think I'm going to be doing anything. Okay. So, is this going to work? Ooh, is it not working? It doesn't seem to be working.
Yeah, Professor?
Yeah.
When I try to install it, including break package system, it doesn't seem to want to work.
Is that ytdlp?
Yeah.
Okay, then don't worry about it. Let's see. Is this file going to work? Okay, so I'm able to successfully download the file. Okay, so I've successfully downloaded a file, and I think if I open this file, it's probably going to open in VLC. There it is. Okay, so I have VLC, which stands for Video LAN Player. It doesn't matter what it is. So this is the WAV file. This is the sound file associated with it.
Gangnam Style.
And we're not going to listen to the entirety of Gangnam Style again, right? That would be a bridge too far even for me. Right. So how can you get that on your system? Well, I clicked the link and downloaded it. This went to my downloads folder. And here it is in my downloads folder. I can also navigate to my downloads folder from the terminal, which I will show how to do. I will go to home or wherever you are. Let's see, if you're on Windows, what are you going to want to do? I think you're going to want to just open this, blah, blah, blah. Okay. I think you want to do this, and then maybe you can like right-click and open a terminal inside your downloads folder.
Well, you should on Windows just be able to do /cd/downloads.
cd/downloads.
From your user folder.
Okay.
Where it starts.
Okay. So do that, and ask Isaiah if you're not sure how to do it. From here, I can type either start if I'm on Windows, or open sci.wav, and it will open inside of my command line. And then from here, it will start playing. Okay, I don't think that's going to work very well on the first try, so is anyone stuck, and can I help anyone with that? Yeah.
I got my ytdlp to work, and also the app. I installed the file, but I don't know what else to do with it.
Which file did you install?
For the WAV file.
Okay, you downloaded the WAV file. Do you know where it is on your computer?
No.
Okay. Actually, I wonder if the better way to do this. I think you want to do this. Okay. So what did I do there? This is a link. Do I actually have this on the next slide? Let's see. All right. This isn't too bad. So I'm going to skip forward over a few slides. Why is that? Last time I taught this class, I taught everyone how to install YouTube DLP and FFmpeg, and it took like an hour. We only have an hour today. So this is how to install YouTube DLP. This is how to install FFmpeg. This is how to install both of them and get them to work together. This will create the file that I created on your device, and I can prove that probably. And it's going to be slow, okay? This is taking forever. Okay. And then, instead of doing that, I also have VLC player installed. I'm guessing you all have something installed that can play music files, right? But I can save you all of that. Go to slide 20, or just navigate somewhere else on the web page. And we're going to introduce the curl shell commands. Curl is a way to get files off of the internet onto your computer. This is often something I use with CSV files if I don't want to be downloading them every single time I run the Python script. So, given a location of a file, you can curl, which it stands for like CURL. I don't know what it stands for. And so what I have here is I have sci.wave. I'm going to remove that. And I'm going to use this curl command. And this is a long URL. That's why I gave it here in a copy-paste block. I'm going to paste that. And what is this? This is the command, curl. It is the URL of the file, which I think I can open that and just go to the file location. Maybe this doesn't work. Okay, we'll find out. And then I have an -o flag, which gives the name of the output, and that is called sci.wave. And then I have sci.wave on my system. And so that was just by using this exact command. I'm going to check to see if sci.wave works. Ooh, that one's not working. Okay. It's supposed to download the file at the location, but I did an earlier curl and it worked.
Oh, there we go.
This one worked. Okay. I'm going to make this big on my screen so you can all see it. Okay. This is what I did. This is the URL of the class. And just right at that URL, there's a sci.wave. And can I go to this one? That worked. Okay. So you can even just put this in your web browser and download it. But otherwise, if you curl this address -0 sci.wave, it will work. And let's wait for at least a couple people to verify they've gotten this managed. You got it? Can you play it?
I can play it.
Okay.
Would you like me to play it?
I guess I believe you.
Oh.
Okay. Oh, you can play it if you want.
Play it, would you say like open?
Yes. So the two things I would do is I did the curl command. It's quite small. Function F11. Okay.
Yep, it plays.
So clear. I curled it. I'm getting the file. It's going to take 6 seconds because I am downloading a video off the internet. It's a 4-minute video, so it does take a certain amount of time. Then I'm going to open sci.wave. You are on Windows, so you might say start sci.wave.
It opened my Apple Music, but it doesn't show.
I don't know how Apples work. I'm going to go just look at your screen.
Oh my god, it worked.
And on the first try,
Oh, it says the file is not supported.
oh, maybe Apple can't open Waves.
Yeah, it plays, I'm pretty sure that it plays MP3s and waves through Apple Music. Like, that's
Okay.
the file opener.
Yeah, mine is not, it says the file is not supported.
Oh, not
And
supported.
I'm a Windows
Okay.
person.
But you got the file.
Yeah, I got the file, just
And you get play it, just yelled at you.
Yeah, it says file not supported, so I actually play it.
Can I see what command you used?
Oh, like,
Just your command. Start. Okay.
because open didn't work.
Yeah. Okay. Anyways, you are all welcome to download VLC Media Player. There's also one other one. You'd have to ask the quad tutors. I think this is like I've been around too long. I think VLC is not the most popular one anymore, but it's like what I have installed
I think
everywhere.
VLC is still arguably the best.
I certainly like it the best, but there's some reason someone else uses another one. I don't know. And I think also there's just like a VLC command line tool as well. So you can definitely get VLC if you want in the manner of your choosing. And that is my recommended way to solve the problem of it potentially not working. But you're also under no obligation to do that right now or ever. Okay. So I'm going to keep moving on, and if you couldn't follow along with this section, that's fine. This was pretty complicated. Okay. So I'm going to demonstrate how I'm going to load a file into SymPy. Let's see. Do I have two of these open? I think I want to be over here. Do I have? Okay, I have sci.wave. Okay. So with matplotlib, with NumPy, with pandas, everyone always imports them by the same name. They call them PD for pandas, NP for NumPy, PLT for matplotlib, pyplot. That is not necessarily commonly how this is done with SymPy. SymPy is huge, and it is unusual that people want to include all of it at the same time. So usually we're going to say, we're going to import a few specific things from a specific part of SymPy, and this is going to lead to names getting longer and complexity getting higher, but I trust you, you're ready to do this. So how am I going to do this? I need to have SymPy.io. So I'm going to create, we'll just use skip actually. I'm going to import SymPy.io, just part of it. What does IO stand for? Input output, and the input output I'm going to do is I'm going to do a WAV file read. What am I going to do? Well, I'm just going to print something first, which I'm going to take SymPy.io.wavefile.read, many names, right? So this is the name of the library, it's the input output in the library, it's the WAV file specific stuff, and then I'm going to read, and I'm going to read sci.wave. I'm just going to set that equal to x, and I'm going to print it out. How am I going to run that? Python skip. So what have I printed out here? There's a few different things going on here, and you can actually inspect this and figure out what they are. I have an open parenthesis, which means that I'm getting more than one thing back. The first value in the open parenthesis is a numeric value. This is 48,000. I believe that is the the update rate for how often the sound changes. I don't know what that means. But somehow this is like how fast sounds are coming out. Then what we have over here is we have an array. This is a two-dimensional NumPy array of integer 16s. So these are integers. As we see, 13, 1, 0, 0. And I'll step through it, but what I found out over time is that actually these are the two stereo channels, so one of these is left and one of these is right. And so that's why there's two of them, because this is a stereo wave file. And so we can look at that and we can decompose all of these things and look at them separately. One way I'm going to do this is I'm going to unpack those two values by giving them two different names. So I'm going to say rate and data are the two things I'm going to get. I'm going to print the rate, and then I'm going to print the data. That's not what I meant to do. So I can print them out separately and see that this is some kind of rate and this is some kind of data. I got this just by looking at the SymPy documentation. They will always have examples, and so I got this from someone else who was doing the same thing. So what is going on here This is giving us the example of multiple assignment. So if I look at this, cat, Skippy, I'm taking two variables and I'm setting it equal to one thing. This is not super unusual to do, and the next most common way to do it is with square rooting. So for example, I can create the function roots of x that will return the roots of x, and I needed to import NumPy first. Did I? No, I could have gotten away with it. Def roots of x, and I'm going to calculate one of the roots. I will find the positive root. We'll call it pos root, which is going to be x to the 0.5 power, which is a way to calculate the square root of something, x to the half power. And then I'm going to return the positive root. I'll do negative first. I'll return the negation of the positive root and also the positive root. And then if I calculate the roots of 25, I will get -5 and 5. This is the same thing that I'm getting when I read the wave file. It's just they're both numbers instead of one of them being a NumPy array. Okay. Now, what I can do is I can capture the negative and the positive value by giving names for each of the two things I get back. And then I can see the negative and the positive value, and this simply breaks if I provide too many things. So, if you know that your function is going to give back two things or three things, you can give it two or three names, and it's called unpacking. You can unpack the values that are given back by the function. In my case, my wave file is giving back two things. It's giving back the rate at which the audio is recorded, and it's also giving back the audio at every time point. We can also, you might want to check the type of negative, which is a float, right? Because it's a -5.0. But we can also check the type of the roots of 25, and that's just called a tuple. So if you ever see a tuple, that's something you can unpack. And I believe you can also unpack lists. So I can say xy equals 1, 2, and I will get my x and y back from the 1 and the 2. I might even be able to do this. Let's see if this is allowed. That's also allowed. So you can do this with boxy brackets, with the standard parentheses, or with anything you like, and it is just a useful tool to be able to do. Okay. So, given that, let's see, do I care about this? We don't have time for this, do we? Okay. Oh, no, I do want to introduce try except. Okay. So, I have previously taught you about lists in the context of, you probably remember taxes, where we have something like 1%, 9275, 0.15%, 37500, something like this. Does that look right? These are the lists we worked with. You can always, instead of using the boxy brackets, you can use regular parentheses. And there's like really only one difference, which is that if I say this is tax list, wow, I have got to turn my sound back off. Sorry?
What does that sound?
Oh, it's me typing things that I'm not allowed to type, and my computer's yelling at me. Usually I just turn the sound off and ignore it, because I do things I'm not supposed to so often. Then we can also have a tax tup. We can look at the tax list. We can look at the tax tup. The thing that I can't do with tuples, which is the thing that returned from my roots function, which is the thing that returned from my SymPy function, is I'm just not allowed to change them. So for example, if I wanted to change the policy to no longer cut off the 10% rate at 9275, but instead at 15,000, I can look up in the tax list where the 9275 lives, and I can update it to 15,000. And that will then change the tax list. This is not allowed for tuples. You're not allowed to change the values inside tuples. That is the only difference between tuples and lists. So if you see this error, and the only reason I'm showing this is so you see this error, tuples and lists are just alike, except lists use box brackets and you're allowed to change them. That's all. Never think about this again unless you have to. Now, there is a helpful thing that this introduces, which is how we can deal with errors in Python. And I wanted to show you what try except looks like, because when we get to using scientific Python, code doesn't work a lot, and usually you intend for it not to work, where you write some code optimistically, hoping that the file is in the format you expect, or that you have enough lines of data or something else, so you're going to try something, and then if it doesn't work, you're going to print something else. So how can we do this? I have my tax tube already, so I'm going to try to set tax tube 0, 1 equal to 15,000, and if that doesn't work, I'm just going to say tuples can't do that, or whatever else I want to say. What will happen here is Python will attempt to run this line of code. If it encounters an error, it will run this line of code, but it won't actually cause an error. Let me give you a counter example. We can also try tax list 0, 1 equals, I'm going to put in a different number than 15,000 because I already changed it, so I'm going to say 10,000, except blah, blah, blah. We'll print blah, blah, blah. In this case, I don't print blah, blah, blah because I don't encounter an error. I think you're not allowed to divide by 0, but you're allowed to try to divide by 0. And then if there's an exception, you print something. So I printed an empty line, right? So this is a way to get around code that potentially contains errors. Okay? This is often used when reading files. So perhaps import SymPy.io, try, see, rate data equals SymPy.io dot, it was the file name, dot read, sci.wave. And if that doesn't work, we're just going to print whoops, and that's fine. This is a good way to do this if you don't know if you successfully downloaded sci.wave onto your computer, right? And then you can just look at the rate, and you can look at the data, no problem. Okay. The reason I added this to these slides is the first time I tried to curl sci.wave, it didn't work, and then my code crashed, and I didn't know why. So I'm teaching it to you now, because it was the first time I encountered it this term. Okay, let's go ahead and look at some of the data. We can look at the first 10. Oops. And it's all zeros. Now, I would like to have you engage your critical thinking skills on this. When I first pressed play on the Psy Gangnam Style video, did the sound start immediately, or did it start after a few seconds?
After a few seconds.
It started after a few seconds, and I forgot that when I did this. I thought my computer wasn't working. But I think it takes almost 4 seconds to start. So what I really need to do is I need to go pretty far through this file before I actually find any sound at all. But this also does suggest all of these zeros represent no sound. So that's something that is interesting. Okay, so how are we going to deal with this? Well, audio doesn't come in for about 4 seconds. The song ends and there's a kind of outro. Why don't I just plot this data? Oh, I didn't import matplotlib. No problem. Import matplotlib.pyplot as plt. Plot the data. That took a long time. There is a ton of data in here. This is one of our biggest data sets we've worked with so far. And what am I going to do with this? Well, I'm going to plt.savefig. Oh, I think there's no underscore. It's just savefig. Sci.png. That will take a moment. I'm going to import os, os.system, open sci.png. And there's my plot. And by the way, it's the same plot I showed on the slides. Huge W for plots being the same. I'm going to full screenify this so it's a little more visible. What's going on here? Do you remember the song starting more quietly than it became after a moment? Perhaps. I think so. I think it like fades in a little bit. So that's that ramp here. 0 comes up right here. We have some blank. Looks like audio cuts out at a brief moment for a few points. And then over here, do you remember the outro? I think someone said, oh, let's do it again, or something like that, right? That's over here. The song ends, it fades out. They like strike the pose, right? And then like the person in the yellow suit comes back and starts dancing again. That's this sound here. Then we get to the end of the video, and there's some more dead time at the end. So this is, in fact, consistent with what we heard. And that's why we had to watch the whole video, so that you could see what this is, right?
So that's just showing the audio, when the audio comes in and the rate is going?
This is a way of visualizing like the amount of sound. It's difficult to visualize the actual sound because 48,000 things happen per second. So really, what this means is that, you know, every couple seconds you're going to hit your maximum volume or your highest frequency or something. But there's also negatives here, right? So I'm guessing these are frequencies that are being played at. I don't actually know how sound works, but I thought it was interesting to look at it, and I could see things that I recognize. Okay. So what does that mean? Well, we can look at the first 10 seconds of data by looking at data. What are we going to do?
Look at data.
We are going to look at data. We are going to take the rate times 10. What is that? I'm going to look at every 10 seconds, I think. And I'm going to look at it by the rate. So I'm going to go up to the first 10 seconds, and I'm going to look at every second until I get there. Oh no, my voice completely vanished. Oh my gosh. Okay. Oh no, I have to teach an entire class after this. Okay. Does one of you want to teach my next class? Oh, it'd be really fun. I think you'd have fun. Okay. What is this looking at? Well, we have around 4 or 5 seconds of no sound, and then sound comes in. We can look at this more precisely if we want to. Oops. Let me see. Oh, look, sound comes in all at once here. Where is that? I don't know. I could figure it out if I wanted to, right? Okay. Why are there pairs? Those two values may look initially suspicious than I remembered. Many mammals, including some assistant professors of computer science, have 2 ears, right? This is a stereo file, and the pairs are for each of 2 speakers. My headphones at home, I dropped them on the floor, and they tore one of the wires, and so I actually only hear sound through my left ear when I'm listening to music at home. It's very sad. Could I buy more speakers? I don't know. I'm kind of like attached to those ones, right? Like, I don't really want to throw something out. Maybe I could figure out how to patch the wires. I don't know. All right. Wait, I heard the sound of you not believing me. I often hear that sound. So I'm just going to spend the last 4 minutes, and I don't think we'll finish this in time. I'm going to split these into a left and a right file. How am I going to do that? Here's the data. What does this do? Let's see, I think I actually have to do regular colon. So, remember how we can look at arrays by looking at different indexes? And you say, hey, give me all of the houses on the left side of the street. So, this is going to give me, when I look at 0, that's actually the same thing as this, which is just the very first entry, right? But I can additionally ask for a slice, and for example, I can ask for 0, 0, right? What I actually want is probably something a lot more like this. This is every value on the, I don't know, on the 0 side, right, at every single time point. And this is every value on the 1 side at every time point. These 3 zeros correspond to these 3 zeros. these 13, 14, 14 correspond to these 13, 14, 14, and then these 1, 2, 3 correspond to these 1, 2, 3. Now, what I can do with these files, or with these arrays, is I can actually just save them as sound files and then listen to them. But in order to do that, I have to transpose things back into a different size. So how am I going to do this? Well, I'm going to take these two data files and I'm going to put them back together as if they are one sound file where the stereo on each side is playing only the left track or only the right track. So I can take the data and I can transpose it, and it looks like this. It's now horizontal instead of vertical. I can look at the 0 of the transpose, and that is the first one. And we can just arbitrarily break these into left and right. I don't know if I want these vertical or horizontal right now, so I'm just going to, whoa, what did I pressed something. Oh, I'm in print view. Okay. So I'm going to create a left, and I don't know if they're left and right, but I just have to call them something. I'm not going to use the transpose here. I'm just going to say data 0. Is that right? That looks good? Okay. And I'm going to call it RITE because I don't know if it's right. Get it? Because it could be wrong. Right? Yeah? 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 Right? Tough crowd. Okay. Here's left. Here's right. Okay. Now, there's a few things I can do, but something that I thought would be the most interesting to do is actually zero out one of the sides. So I'm going to import NumPy. Oh dear. Import NumPy as NP. I'm going to say 0 equals NP dot 0 equals NP dot zeros. Length of left. And I'm going to, I think I have to specify the data type. Maybe I don't have to specify the data type. I don't know. So here's 0. It's many zeros. And then what happens if I add left plus 0? Let's see. What is left to 0? It's going to do a vectorized operation. And that's not what I want it to do. I want to combine them together. So instead, I'm going to need to create an NP array of the lefts and the zeros, which I will do as follows. NP.array left, nope, I have to put them in box brackets. Okay, left 0. And that creates a zeroed out left, and we'll call it there for today. I have the sound files here, but I wasn't able to play them in my browser. So, wait, is this one working? It's only coming out of this side. I don't know if you can tell.
Gangnam Style.
And then if I play this one, it'll only come out of this side. I think. It'll be really embarrassing if that's not true. See. Okay. See you on Friday. Thank you.